All right, we are now recording. Let's start from current slide. Okay, can't think of any announcements per se. Any questions on anything we've covered so far? Now, did all of you get copies of the first test? You didn't. Okay. I think I have spares, but yeah, here it is. For those who weren't here at the end of after class, I'll say, last time, we did, I forgot that this one had an error on it too. Number 7, it says how many rail cars weighing 45,000 pounds each. That should be 4,500 pounds each, not 45,000. Okay? Let's see. I don't even know what is reasonable on that. What you could do is increase the pulling force to 175,000. I don't know which one they intended, but let's keep it easier and make 4,500 pounds each. That would be 2.5 tons. Oh, no. A little over 2 tons. That may be unrealistic, but it'll do in the pinch. All right. Okay. Were there any other changes to this? I know we talked about several problems, but I don't think we made any changes, did we? Okay. That was the only one. Okay. All right. All right. Where we left off last time, we finished 8.1, which was power. 8.1, which was what, work, I believe it was. Yeah, work and energy. Well, that's the whole chapter, is work and energy. 8.1, I think, was just work. Well, where is 8.1? Yeah, 8.1 was work. And this is CC, right? Okay. Okay. So, 8.2 begins with power. Anyone want to offer a definition of the difference between work and power? Or the relationship, the connection between work and power? Oh, yeah, we left the door open. Okay? We use the terms almost interchangeably, don't we? Okay? In reality, there is a difference. Okay? Let's think back to when we were talking about distance and time. How were they related? Time rate of change of distance was speed or velocity. Time rate of change of velocity was acceleration. Time rate of change of, do we talk about momentum? We may not have. But anyway, we do that all the time in physics. Once we get a thing that we understand, work with, and say, well, what about the time rate of change of that? How fast does this happen? Okay, that's what power is. It's the time rate of change of doing work. Okay? So the formula, the rate of doing work. And that formula is power. Oops, let me get my pen set up. Power is equal to work over time. Now remember, capital W is work, little w is weight. Okay? So this is capital W, work. Where P is in power, W is in work, and T is in time. Let's talk about some units for that. What is our SI unit for work? Anyone remember? Joule. Very good. So the unit would be joule, and what's the SI unit for time? Seconds. So a joule per second. Well, that has a name. Anyone want to hazard a guess? As soon as I say it, you'll probably think electrical. Watt. Yeah, watt? Watt. Okay, yeah, we got it. This is what a watt is. But guess what? That's a capital W. Now that capital W is a unit. It's for power. the capital W that's a parameter stands for work. It's not a unit. The watt would have a number in front of it. The W in a formula would not. That's just work. Okay? Why is it capitalized in? Units named after James Watt. Okay? Now, when James Watt was working, he dealt in U.S. customer. Actually, it was then called the British system. So he didn't use watts, he used horsepower. In fact, he's the one that defined what a horsepower was. Horsepower is a measure of power. But in the SI system, it's joules per second, which is a watt. Okay? Now, a joule is a very small amount of energy. A second is a very small amount of time. So a joule per second, that's really tiny. Okay? So, usually we use with bigger units than that, especially electrical. You never, or seldom, well, you do talk about watts and bulbs and things like this, but if you're talking about your bill at the end of the month, it's measured in kilowatts, and kilo stands for 1,000. And if you're talking about power plants, you usually refer to them as megawatts, and mega means million. Okay, K, kilo, is 1,000, M, mega, is a million. Okay, so that'd be millions of watts. Okay, now in the U.S. customary, what's our unit for work? Second? No, what's the unit for work? Work is still capital W, but in the U.S. customary, what's a unit for work? You had it in one of your problems. Foot-pounds. That's foot is distance, pounds is force. Force times distance, that's work. And the unit for time? Second. Foot-pounds per second. Okay? It doesn't have a special name. Now, James Watt is featured, an engineer and inventor born in Scotland. He made fundamental improvements to steam engines, accredited with several related inventions, and he came up with the definition of a horsepower. And what his goal was here, that should measure what an average dray horse, that's the working horses, could do in a day. So how much work it could do in the day would be 1 horsepower. Well, this is in seconds and foot-pounds per second. So here's what it turns out to be. 550, this is not SI, so the numbers are weird, foot-pounds per second is what 1 horsepower is. No, that's not, yeah, 550 foot-pounds per second. Okay? If you multiplied that by 60, that would give you 33,000 foot-pounds per minute. If you multiply that by 60 again, you get per hour. Multiply that by probably 8 or so, that would give you how much work a dray horse could do in a day. Okay? That's where he started. We are not going there. We're going to leave it as 550 foot-pounds per second. All right. Now, nice little blurb here. Seeing if they had any things that related the two, but they don't really. How much equivalent horsepower do you possess? Okay. So what you can do is take a tape measure, stopwatch, a flight of stairs, determine the horsepower in your legs when climbing the flight of stairs. First measure the vertical height of the stairs, use that distance and your weight to determine the work done, and then the time, how long it takes you to walk or run up the stairs. And you can convert that to horsepower. And what would be the horsepower of a lawnmower? I don't know for sure. Probably a bit more than you're climbing the stairs. Of a car, much more than you're climbing the stairs. Okay. And by the way, if you're in either my physical science class or physics class, we do that lab. But we're not doing labs in here. It's always a sort of a fun lab to do. All right, let's look at example 1. I'll clear this screen if y'all are okay with it. Okay, a freight elevator with an operator, okay, weighs 5,000 newtons. And they put the bar over the middle zero, that's newtons. Now, they tell you that's a force. And they usually put the sub W, meaning the weight, the force due to weight. This time they don't. If that freight elevator is raised to a height of 15 meters, 15.0 meters, okay, so the height, or you might say distance, or you might say S for distance, whatever you use for height, is 15.0 meters. Now, just give an idea of what that is. I'm approximately 2 meters tall, a little bit less, but pretty close to it. And above me is about another meter, right? So about 1.5 of me would be to the top, right? So this is 3 meters. So for 15 meters, that would be a 5-story building, approximately. Maybe a little bit, or so this is raising it 5 stories. A freight elevator weighing 2.5 tons, raised to a height of 15 meters. Now it says it takes in time of 10.0 seconds. Okay? Now, the question is, what was the power needed to do that? How would you get that? Say again? Multiply what, by the way? Okay, exactly. Because your weight is always downward toward the center of the earth, and since you're raising it up, you're working against that weight, so there's the force times the distance. That gives you what? Force times distance is, oh boy, how long time ago we did that, right? At least 2 days. Force times distance is? Oh, come on. 75. Okay, yeah, but what is force times the distance? Force times the displacement. What was the title of the last section we did? No, that's the last chapter. Work! This is your work. Force times the displacement. Remember me digging on the rock. Didn't displace it, did no work, even though I exerted a lot of force on it. So that gives you that. So that would be, we'll do it in pieces, okay? Then what do you do to get power? You're right. That's work divided by time. So this will be your work. Goodness gracious. This thing keeps flipping around. That would be, work is 5,000 with the middle digit there, newtons, that's your force, times your, this is so aggravating, times your displacement, which was 15.0 meters. Goodness gracious, it just moves. 15.0 meters. That multiplies to be your work. Divide that by time, 10.0 seconds. And what do you get? Well, here's one way to do it. All 3 digits. So I'm going to take out 1 here and take out that one. So 500 times 15 would be 7,500. So that would be 7,500. What unit? Second? Okay. A newton meter is a joule per second. What's a joule per second? So you could, okay, wait, you're right. I see what you're saying. Newton meter per second. That's exactly legitimate. Now, by the way, I need to put something over one of those 2 zeros, don't I? Which one? The first one, okay, because we have 3 digits here, 3 digits there, 3 digits there, okay? What's another name for Newton meter? A what? Joule. So that would be 7,500 with the bar over there, joule per second. And what's another unit for joule per second? A what? A watt. Okay, got it. Okay. 7,500 watts. Okay? Now, to keep from having to carry all those zeros around and commas and things like this, and to keep from having to put that zero on top of that bar on top of the zero, you could change this to a bigger unit and give a smaller number. What would be the bigger unit? Second? I can't hear it. Kilowatts. And how many kilowatts would that be? 7.50 kilowatts. See, if you put the zero after the decimal point, you don't have to put a bar over it, because any zeros after a decimal point at the end will be significant. So that is the easiest way to write that problem. Because you're in SI system, you can do that. If you're in U.S. customary, nah.
So you're saying it's 7.50, or you just, your zero is just automatic right there, you crossing out zero?
Oh, no, no, I always slash my zeros. When I was in the Navy, we had the slash, in keeping logs, you slash zeros, slash sevens, and slash Z's. Because Z could look like a 2, and you didn't want to get those confused. 7 could look sort of like a 1, so that's why you kept that. And a 0 could look like an O. So when you're keeping logs, and logs are the official documents, you had to make sure it was clear that you're talking about a number rather than a letter, or vice versa. They left it as Newton meters per second. Okay? So you didn't have to do all that other. But just in case you ever run into answers in the back or something like that, all those are correct answers. Okay? Now, how about let's go into another problem? Okay? All right to erase this? Okay. Example 2. The power expended in lifting 825-pound girder. 825 pounds. What's that a measure of? A little louder? Weight, you said? Yeah. And that is the force due to weight. Okay? Little w weight. Okay? To the top of a building 100 feet high. So 100 feet. We have been calling that your displacement. It could be called height. It could be called Y because it's up. It could be any of those things. But generally, we call it displacement. Okay? And it's in the direction of the lift. The power expended is 10 horsepower. So 10.0 horsepower is the power expended. Okay? How much time is required to raise the girder? So what we're looking for is the time. So we're going to need to find some way to relate the time with those other units that we were dealing with. How? Basically, same formula you were using. What was that? Power is equal to, a little louder. Okay, it's not weight over time. Work over time. Work over time. But what is your work? Oh boy, so long since we did that. Force times a distance. Yes, so that's the force times the distance, and that force is the weight divided by time. Okay, there's a formula that relates force or weight, displacement, and time, and power. But this one we want to solve for time. So how do we do that? multiply both sides by time, okay? Because I don't like having time in the denominator, okay? If that's what I'm solving for. But now what we need to do, we want to isolate the time. So how do we do that? If time is multiplied by power, how can we isolate the time? How do you undo multiplication? Divide. Divide both sides by the power. Okay? So now we have, now the powers go away, you have time is equal to force due to weight times displacement over the power. Now, you could have developed you kind of a fat little triangle or circle, because now you have three things in it, not just two, but you could have done that if you wanted to. So now we plug and chug. We've already, or maybe we chug and plug, whatever. So whatever. What is your force due to weight? 825 pounds times 100 feet. That's your displacement. Divided by 10 horsepower. Whoa, that's horsepower. We got a problem, Houston. The numerator is foot-pounds. The denominator is horsepower. Okay? What is a horsepower, though? Okay? This would be, yeah. So I think I would have, perhaps up here, let's convert here. Okay. Okay. Let's start by getting our units right. 10.0 horsepower. Okay. And you just, I heard someone say 1 horsepower is what? And 50 foot-pounds. Okay. So we're going to multiply here, so your units go out, divide by that, so this will be how many foot-pounds? What's that? I can't hear.
It's getting confusing.
Okay. All right. Someone just told me, let's start over again. Okay. That 550 foot-pounds is equal to, foot-pound, I'm sorry, I left off the second, per second, okay, okay, is equal to 1 horsepower. Yeah, you're right, that's 550 foot-pounds per second, okay? So, we know that is the conversion. We had 10.0 horsepower. Okay, we're going to need to multiply. Remember how we did our unit conversion? We're trying to get this to be foot-pounds per second. Okay? Okay. Okay. First, always put the units into place. Right? Now, what unit is going to go where to make that conversion? Something goes below the line, something goes above the line. What goes where? Just to make the units work out. Always do the units first. Don't worry about the numbers yet. Second? Something goes in the numerator, something goes in the denominator.
So are you going from 10.0 horsepower
to foot-pounds per second. So something goes in the numerator, something goes in the denominator. One of those somethings is this, and one of the somethings is that. Horsepower has to go in the bottom, so it'll cancel out. And you want foot-pounds per second on the top, because that's where it winds up being, right? Okay. Now, since you know the conversion over here, right, 1 horsepower is equal to 550 foot-pounds per second, right? You told me that to begin with. So match the numbers with the units. Now do your conversion. You multiply numerators, divide by the denominator. Denominator is 1. I can divide by that easily, just 1. So what is 550 times 10? 5,500 foot-pounds per second. All right. So instead of 10 horsepower in that thing, I'm going to put 5,500 foot-pounds per second. 5,500 foot-pounds per second. This thing is driving me nuts. Okay. All right. I'm going to take some of this out of the way because it's getting sort of crowded here. This is a problem with having such a small screen to work with. You got so many foot-pounds per second in there. Okay. You don't have to erase yours. I'm just erasing mine so it'll be easier to see. Okay. Now we do the math. Okay. Actually, first, I'm going to cancel units. The feet cancel feet. The pounds cancel pounds. Okay. And actually, I'm going to make the numbers easier to deal with. Those 2 zeros and those 2 zeros. So what that leaves me with is 825 divided by 55. Anyone punch that in a calculator and see what you get? 825 divided by 55. 15? Okay. Is it 15 on the nose? Second? Okay. Well, it looks like to me, and I may not have written it down correctly, but let's see. Yeah, the 100 feet did have a bar over it. Okay. Everything had 3 significant digits, including the 550, I think. They don't put it over it, but I believe that's how it's defined, exactly 550. So that would have to be 15.0 then to get your number of significant digits. Now, what are the units? They're seconds, exactly. Because here you have no units, so just 1. Here you have 1 over second, and 1 divided by 1 over second, that would be 1. This is just units now, divided by 1 over second is the same as 1 times second over 1, and that's just seconds. So yeah, 1 over 1 over second is a second. Okay. This is just dealing with the units. Just treat them like fractions and they work out. 15 seconds. Okay. See what they got. Yep, good for them. Now, well, okay. I was just being lazy because I don't have a calculator, and I was just making it easy. Okay? But you see, you could divide by numerator and denominator by 100, it's fine. That's what dividing up 2 zeros does.
Yeah, my calculator came up to 150, so we had to put the decimal after 15.
Okay, it shouldn't have come up to 150. Did you do all your... Okay, what did you put in your calculator? 825 divided by what? 50? No, 55. Okay, wait. Okay, did you keep the 100 up there? Okay, do 825 times 100 divided by 5,500. Do that. No, it's 5,500.
See, we did 55. I did 5,500. That's how I came up with the 150.
Okay, no. Do it. Punch it in. 825 times 100 divided by 5,500. Okay. Okay. I think what you did was divided by 550. But we 550 pounds per second is 1 horsepower, but we had 10 horsepower. That's why we multiplied by 10. That gave you 5,500. In fact, one of you told me 5,500 times. But when you put it up there, you put 550. So it's 5,500. Good deal. What's that? Well, guess what? Some problems are longer than others. But, you know, how do you eat a 5,000-pound elephant? One bite at a time. Just take it in little bites and deal with it each little piece at a time, and then you'll have a smorgasbord. Okay. All right. Now, they show here in the book, and I see several of you have books now, that how they did their conversion. Foot-pounds per horsepower times horsepower per foot-pound per second gives you foot-pounds per horsepower. Boy, they make it seem so complicated, but it comes out.
That's why we're looking at it. That too, it just, I don't know, all this F and T's and ones and B's. And just give me the number.
One bite at a time, okay? Now, if you don't have the units, you might divide where you need to multiply, and you'll never catch it. The units are your friends. Don't leave them off, okay? Yeah, to me, that is a bit bizarre, okay? Okay. Let's try example 3. Can I erase this one? Okay. Example 3. The mass of a large steel wrecking ball is 2,000 kilograms. They said that the mass is 2,000 kilograms, and they put a bar over the middle zero there, kilograms. What power is used to raise it to a height of 40 meters? So your height or your distance is going to be 40.0 meters. Okay? If the work is done in 20 seconds, what's that a measure of? Time. Perfect. Okay? Now, they're asking what is the power. So that's your unknown. Power is the unknown here. So how can we relate mass, distance or height, and time? And power. Guess what? Not directly. Say again? Okay, sort of. Tell me what equation you're talking about. Power is equal to? A little louder. Force times the height or distance divided by time. And where's the disconnect here? Second? Oh, yes, you do. Look at the parameters you got in your formula and look at the parameters you got up above. By what? Oh, wait, okay. So we've got a new formula for power. It's mass times displacement divided by time. Is that right? They had it wrong in the book. No. Oh, yeah! You don't know your force, do you? And what force are you talking about here? Force due to weight or gravity, so that's F sub little w. And what is it? M times G. Yes, gee whiz, we got it right. What's that? I couldn't hear. Acceleration due to gravity. Right, so the mass is 2,000 kilograms times 9.80, I believe is what the book uses, isn't it? Meters per second squared That was the previous chapter. Hey, just because we left the chapter, we don't mean throw it away. This is a history class. This is an art class. When you finish one, forget that, go on to the next. This all builds on itself. Okay? So, that gives you what? Or you don't have to actually give the answer now. You could just plug that in down here. Whichever you want to do. Want to just plug it in down here? You want to go on and do it? Okay. Oh, up to you. You paid your money, take your choice. Multiply, and what do you get? Second? Okay. Newtons, you said, okay? Very good. Kilogram meter per second squared is a Newton. So that's your force due to weight here. Okay? So that would be 19,600. Notice, what, do we put a bar over either of those zeros? No, because those are the three significant digits right there. Newtons times what distance or displacement? 40.0 meters, and that's divided by 20.0 seconds. Now, you want me to see my lazy way of doing it? Yes, I'm going to show you. 20 will go into 40 twice, won't it? And then multiply by 2. That gives you 30. Not the seconds, just the numbers. Okay, I kept the things there. 20 will go into 40 twice. That's easy. Then multiply by 2, and you get 39.200. And what units? Newton meter per joule. Newton meter per second is a what? A watt. Yeah, capital W. Okay. Now, if you don't want to carry around that big a number, you could go with a smaller number, a bigger unit, because this is SI. 39.2 kilowatts. Very good. Okay. And that way it's obviously how many significant digits. You don't have to worry about, did I put a bar over the zero or not? No. 39.2 kilowatts. Let me see if I can find it. Yeah. Either 39,200 watts or 39.2 kilowatts. Good deal. Make sense?
Now, which one would you accept without going all the way down to kilowatts?
Oh, you could leave it as Newton meters per second. You could use it, leave it as kilogram meter per second squared per second. Okay? No, kilogram meter squared per second squared. Okay? Any of those will work. Or per second cubed. I mean, if they're right, I accept it. Okay?
But you want to reduce it to the 2 with the 0 behind it, right? So then it would be 39,215. So what, it's still going to be 39.2?
Yeah. With no mark over these two, you only have 3 significant digits there. A bar over it means that 0 is significant. Okay? Now, if the 0 is after a decimal point, yeah, usually it's significant. Like, this one's significant, that one's significant. Because these are significant, you don't need to put a bar over the middle one. Everything between 2 significant digits is significant. But here, you have to specify. If you had no bar there, that would only be 1 significant digit. Right there would be 2, that's 3, that's 4. Okay? So you put your bar over. You only have to worry about that. Now, you could have done it this way. I'm not suggesting that you do, but you could have written that one as 2. I say 2 and write 3. There's something wrong with my brain. Okay? You could have written this as 2.00 megagrams. There's no reason to do that, but there it's obvious that's 3 significant digits. You don't need the bar then. Because you moved the decimal 3 places, that jumped you up from kilos to megas, millions to thousands, thousands to millions. Okay? But if you don't have that, you need a bar to designate. But this way, so you didn't have a bar, that was good, or just put it 39.2. It's really clear of 3 significant digits. You can't say, did they leave off a bar there? Do we need a bar? Nah, 3.2. All right, that was example 3. Ready for example 4? Yes, okay. Such enthusiasm I've never seen. Okay. All right. Example 4. A machine is designed to perform a given amount of work in a given amount of time. A second machine does the same amount of work in half the time. Find the power of the second machine compared with the first. Actually, I feel like telling you a dumb story first. Is that okay? Okay. Remember my digging in the patio. Okay? Oh yeah, some of you weren't here last time, so if you weren't, too bad. You'll have to listen to it on YouTube. Okay. Now, I dug on that patio. Remember, I had the first 5 weeks of the summer term, I was just working 2 days a week, so I worked on it some then. But the last 5 weeks, I had off, and I was working on that patio, digging out the patio most of the time. Unfortunately, it didn't rain much that summer, so the ground was really hard, but I didn't have an excuse. Oh, I can't work, it's raining. So I had to work most days. May have had a shower, too, that I got out of. But anyway, it was one hot, dry, hard drop, okay? So I worked and worked and worked at it, and come the end of summer, and may have had an extra weekend there before the next term began, Labor Day was coming up. We were starting the next quarter right after Labor Day, and I only had maybe 3/4 of the way, 2/3 of the way in, but the deepest part was still to go. So I figured I had dug about half of the soil out of the patio in those 5 weeks. So no way, once school started, I was going to be working full time. I'd only have a little time maybe on Friday and weekends, and that would be all. And my wife had plenty of other jobs planned for me. She said, we need to get this finished. Well, one reason I started digging anyway is there was no room to get anything else in there, like a bobcat, because there were trees and house and, and garage. It was just not room for it. But by the time I had dug out 2/3 of the area, there was room to get a bobcat in and get to work. So we called around. Sure enough, found a bobcat for hire, and the guy came out, and he came out. I think it was Labor Day morning, and he came out in about half a day. He dug out the rest of it. Okay. Now, what's the difference? We moved the same amount of soil. So what was the same about that? The work was the same. I moved a certain amount of soil, he moved a certain. Now, time out. I'm going to give myself a little more credit. I took the soil and hauled it down and was building terraces while I did it, okay? But all he did was dump it up to the side. Later, I had to shovel that back in the wheelbarrow and move it down behind the terraces. So he wasn't doing quite the same as me, but, just for getting the soil out, we did move the same amount of soil. Did the same amount of work. What was the difference? Say again? The time was the difference. I took 5 weeks, he took half a day. It's not that funny. Okay. Now, what was different between me and the bobcat? The power. The force was the same. We moved the same amount of soil. The work was the same. What the difference was the time rate of doing work is the power. That bobcat, by the way, I'm working that kind of stuff, well less than half a horsepower. Probably about 1/3 of a horsepower, if not less. That bobcat, probably hundreds of horsepower. So yes, he had a lot more power than I did and got it done. Now, for the next several weekends, I was shoveling the soil and moving it down behind the terraces, but that was not counting, okay? So, that's what we're dealing with here. A machine is designed to perform a given amount of work in a given amount of time. A second machine does the same amount of work in half the time. Find the power of the second machine compared with the first. Okay? Now notice this one has no numbers except half, okay? Half the time. And they spelled it out so you couldn't even recognize that. Okay? So let's see what it says. A machine is designed to perform a given amount of work in a given amount of time. Second machine, so let's say machine 1, okay, does work 1 in time 1, okay? A second machine does the same amount of work. So here's machine 2, and it's going to do the same work. So let's just take off the 1 there because it's the same work for either one. So it's going to do the same work, W, in half the time, 1/2 T1. Well, since we don't need a T2, let's just take off the 1s there too. 1/2 T, okay? Find the power of the second machine compared with the first. So let's first do machine 1. What is power 1 for machine 1? How do we define power? Work divided by time. That's it. So there's your power 1. Let's do the power for machine 2. Okay? And what is it? Same work divided by half a time. Okay? Well, I want to get rid of that 1/2. So how do I do that? I don't like having a half in the denominator. I don't like 0.5 either. That's a decimal. How do I get rid of that in the denominator? How do you get rid of something with a denominator? Multiply by 2. But if I multiply the denominator by 2, I've got to multiply the numerator by 2 too, right? 2. That's a strange thing to wear. So here, that goes to 1, right? So now we have 2 W over T, which is twice the power of 1, not I, okay. Because power of 1 was W over T, so if he did twice as much, if he did the same work in half the time, he has twice the power. Okay, just like if the Bobcat did same work in 1/10,000th of the time, he has 10,000 times more power. No, not that much. What's that? I can't hear it.
I said, when would physics start making any kind of sense?
Oh, I thought it already did.
No.
Oh, okay.
No.
Okay. Well, I mean, is there anything that doesn't make sense with that? Anything I can clear up? Okay. Okay. All right, all right, to erase it? Yeah. That the power of machine 1 is twice the power from machine 2. Yeah. Yeah. Because did it same work in half the time, it had to have twice the power. Okay. All right, to erase? Okay. Let's do example 5. A motor is capable of developing 10.0 kilowatts of power. That's the power for that machine. How large a mass, so we're looking for mass now, this is the unknown. How large a mass can it lift 75 meters? So 75 meters, that's a 0.0 meters. That is a what? I'm sorry? Height or distance, yeah. H or D, either one, whatever you want to use. Okay? And in 20 seconds. So 20.0 seconds, that's a measure of time. Okay, here we go back to one of these. This time we're looking for mass. So, like I think I've heard you say before, same formula, but you just got to break it down maybe a little differently. Because what are we missing here? Second? I'm sorry. Okay, yeah, we don't see a force. How can we get a force out of what we've got here? By what? What force are we dealing with? Notice we are lifting. Lifting. So you're dealing with weight, exactly. That's the force you're dealing with. So how does force or weight deal with these other things here? What is the connection? All you do, I think you told me last time. Hasn't been but about 15 minutes since we did a problem very similar to this, only that one we were solving for time. And they gave us the mass. Okay, yeah, what is weight then? Force due to what weight is. Say that again. Okay. It has nothing to do with the height. What does mass, force, weight have to do with? Give me a formula for it. M times G, that's it. mg. Perfect. Okay. There's your weight force. Is that what you said? I can't hear. I'm sorry. Oh, she said it. I can't hear well, so you have to speak up. Wake me up. Whatever. No, okay. So, now can we write our formula down? Yay or nay? What formula have we been using? Power is equal to F sub W, that's the weight. I don't think so. Work divided by time. You want to back up and say that? Okay. We can say that. Okay. It's work divided by time, but what is work? We had that too. Last section, just 2 days ago. What's work? We've done it several times a day. What's work? Force times distance, displacement, yes, divided by time. But what did we just say the work was? Yes, you do. Oh! I want neon lights, but I can't get neon lights on it, huh? Mass times acceleration due to gravity. So that's mg d over t. There it is.
I think it's the wording on how you word it, because each time you ask for something and we looking for something different when it's there all the time. I want to call them W's the weight, but it's not the weight. It's more it's the
Okay, the little w is weight, the capital W is work.
That looks like a little W. The force W. The SW is weight.
Is weight.
The W by
The
itself
force
is
due to
work.
weight. Yeah, W by itself is work. Yeah. And I think that was chapter 5.
Yeah, but it takes time. You are proficient, and you've been doing it for years.
Yeah.
It's something new, so it's gonna take time for us to learn the formulas and what all that stuff.
Right.
I mean, I ain't trying to be funny. I'm just saying it's easy for you. You probably don't understand why we don't understand.
No, no, no.
But you've been doing it for so long, so it's just like that.
Yeah.
But it's not for us.
Yeah. Well, what I'm saying is, I walked you through it, and there it is, right there.
I don't care how much you want to do. It's still new.
Yeah. Okay. So there we have our formula in terms of what we know and don't know. We're solving for mass. That's what we're looking for.
Okay, I have a question.
Yes.
Okay, so like looking at the book, like the basic equation they have in the book for example 5.
Right.
So it has like power equals work over time, and then it has and work equals
Force times displacement. We use D, they use S.
Like, so where's the S coming from?
Well, they use S, they use it up here, we use D or H. Yeah. It's just force times the distance.
That's what my confusion was coming in. I'm like, was the S something different than what we've been using?
No. It's just that. Well, you see, in this, I can't remember where, but for I think when he was talking about work in the last section, I think he used work equal force times displacement. No, he used S. He used S. I'm sorry, I should have been using S then. They spell it out, displacement, but they put S in there. So I'm sorry, I should have been using S.
I'm just trying to make sure I'm not losing E and turn it to an S. So the displacement in the book has actually been S all along.
Yeah, it has. I forgot they used S. I'm so used to doing force times distance, FD, but you can use S. I mean, it's just another parameter meaning the same thing. Okay? So we can change that to S if you want to. I'll put equal S, and here I'll put S, and here I'll put S. Okay. Whoa. All right. So we want to solve for M. Now here is the easy way to do it mathematically. Isolate the M. We want a naked M there. We don't want anything else around it. Okay? Now, it has a T divided, so let's multiply by T. So power times time on that side. Okay, you still got the G, so let's divide by G, but if you divide there, you divide here too. So those go away. And then you got your S, divide by S, divide by S, and the S's go away. And that leaves you mass is equal to power times time divided by G times displacement, distance, whatever you want to call it. Okay? Your power was 10.0 kilowatts, right? Times your time was 20.0 seconds. 20.0 seconds. You're going to divide that by G was 9.80 meters per second squared, and your S was 75.0 meters. Okay. One problem, folks. It's a unit problem. The kilowatts don't match anything else in there. Second? Okay, you could easily change it to watts, or just do 10,000. That would be 10,000 watts. But you still got to get the watts into other units. What is a watt? A watt is a joule per second. But what's a joule? A Newton meter, remember? So that's a Newton meter per second, right? Okay. But what's a Newton? It's a kilogram meter per second squared times a meter per second. Okay? A Newton is that, and that times a meter per second. So now we got units that match up. Okay? No, I mean, this is just the same units. Y'all knew these before. Okay? So what we're going to do, rather than kilowatts, we're going to call that, drives me nuts, 10,000, because that's what, and only that second zero is significant there because here, the other two just have to make 1,000. And that's watts, but a watt is a kilogram meter squared per second cubed. Okay, pretty weird units, right? Okay, times 20.0 seconds. Come on, show up seconds. There we go. That second will wipe out this one of those seconds and get us back to seconds squared. Okay. Divide this by 9.80. I don't know why the 9 disappeared. Okay, 9.80 meters per second squared. And this is times 75.0 meters. Okay, I know the units look like they're taking up a lot of space and maybe looking confusing, but here's where they come in to play. Okay, we already wiped out that second over there, so that's out of here. Here we have a meter here, and there's a meter. A meter times meter is meter squared, so that disappears. Here we have a per second squared. There's a per second squared. Hey, that leaves us only kilograms. What mass measured in? Kilograms. So the units are right. That makes you feel all warm and fuzzy like you must have the problem right. So now all you have to do is multiply things in the numerator, divide by things in the denominator. You can do it any way you want to as long as you do those steps. Okay? So basically what I would do is 10,000 times 20. That would be 200,000. Okay? Divided by, and we know the answer is in kilograms, divided by, and you can either, if you're doing it on a calculator, the easy way is to do 200,000, first divide it by 9.8, then divide that answer by 75, and that should give it to you. You can multiply them out and divide by that if you want to. It's so much easier just to 200,000 divided by 9.8, then divide again by 75. And what do you get? A big number. Because that's a lot of power, that's a big distance, and that's, you know, a fair amount of time, but not that much time. Say again? Okay. You know my hearing is so bad I won't ever do it. Okay, I'm sorry. It's all right to yell at me. Okay. Okay. So she got, oh, I see. You got 2,600. We got 3 digits everywhere, so count 3 digits. 1, 2, 3. Look to the right. That's more than 5, so that makes it 2, 6, 7, 0. Show up. Okay, there it is. Kilograms. Okay, I don't know if that's the answer.
It's 272. When he said you divided 2,000 into this first, then after you hit the equal, then you divide it again by 75. It came out to 272.108, and that's what the book has, 272.
Wait a minute.
Well, I did the 200,000. What I went on to multiply the 9.8 times 75.0. See that 735 divided by 200.
Oh, whoa. You're right. What did I forget to divide
You
by?
got 200,000, and we divided 200,000, but the book saying 26. The 4 is 2670.
Okay, that's so far. Did you divide again by 75? Or 9.8? No. Did you divide that by 9.8? Oh, okay. That's not kilograms, then. That's newtons. Okay. This is Newton, and when you divide that by 9.8, you get 272. Okay. Okay. Divide that by the 9.8. You didn't divide by 9.8. Okay. 9.80 and that'll be meters per second squared. And that would give you, what did you get as the answer? Okay, what did you get as an answer? 272, that's what they got, 272 kilograms. That's a pretty fair mass, okay? 272 kilograms, that would be, multiply that by another 2.2, that would be close to 600 pounds, okay? Okay. Yeah, the book broke it down into smaller steps, but we did the same thing. If you'd done it my way, you'd have done all the math at once. And, okay. All right. But, I mean, it's the same thing. It's just whether you break it down or run it together. What? All right. Let's look at example 6. Ready? Can I delete this one? Yep. Okay. A pump is needed to lift 1,500 liters of water. 1,500 liters of water. Now, what's that a measure of? It's a volume measurement or a capacity measurement. So this is going to be volume. Now, capital V is volume, little v is velocity. So again, we have a lot of things to keep up with in too few letters. So capital V is volume. Okay? Is needed to lift that much water. Oh, liters of water per minute. Okay? This is per minute. So this is volume per time. Okay? Sorry, I didn't read far enough. A distance of 45.0 meters. So what you want to use that? The S is equal to 45.0. What is it? Seconds? Minute? Oh no. No, distance. Okay, sorry about that. Okay, that's meters. That should be a meter. Yeah. What power, okay, so we're looking for power here, that's your unknown, and they want it in kilowatts, by the way, must the pump be able to deliver? And they give you a little hint here that 1 liter of water, this is only good for water now, 1 liter of water has a mass, I'm going to put 3, equivalent to 1 kilogram of water. Okay? Now the reason for that's true is that way back in the beginning, when they identified a distance of a meter, and then a centimeter was the 100th of that distance, okay? And then they said a cubic centimeter, which is a very small little cube there, little bitty cube of sugar, say, that was 1 gram. That's how they defined what a gram was. Well, a cubic centimeter is the same as a milliliter, and so 1,000 cubic centimeters would be 1 liter, and 1,000 cubic centimeters would be 1,000 grams, which is a kilogram. Okay, so that's where that comes from. That's the same. So that's how we get from a capacity or volume to mass. Okay? Now, so this is the same as saying 15,000, because it's the equivalent measure, kilograms per minute is what the weight of water. The volume of water is liters per minute. The weight of water is kilograms per minute. Okay? Now, they want your answer in kilowatts, right? I believe that's what they say. Okay, kilowatts. Now, you tell me what a tell me first what a watt is. A watt. What is a watt? In units. Okay, a kilowatt is 1,000 watts. Okay, I'll buy that. Okay. And what is a watt? Joule per second. So that's 1,000 joules per second. Okay? Now, someone needs to remind me what a joule is. Oh, y'all remember this? Joule is a joule. A watt is a joule per second. What's a joule? We've done it a couple times today already. I think I heard someone say it. A Newton meter. Remember that? Force times the distance. That's work. So this is 1,000 Newton meters per second. Okay? Just getting all this down. Now, we still got to get from Newton to kilogram. Okay? So we'll come back and get there in a minute. I just want to remind you what kilowatts are. We'll come back and get that if we need to. Okay. Now, you'll notice that your power and your units here are all measured in per second. This is per minute. So we need to convert that 1,500 kilograms per minute into kilograms per second. Right? Because everything else is in seconds here. So how do we do this? Go multiply some numbers, but we don't do those first. We deal with the units first, and we want to get this to some number in kilogram per second, not per minute. So you tell me what unit goes where. Always put the units in their place. Trying to convert from minutes to seconds. What unit goes where? You should. Look at it, huh? One of those on top, one on the bottom. Which goes on top? And they're only dealing with minutes and seconds. What goes on top, what goes on bottom? Oh, sure, you don't have to look anywhere. You're wanting the things to cancel out. So what's going to have to go on top? Second, minutes got to be on top. And that puts seconds on the bottom. The minutes cancel out, and you should get 6 kilograms per second. Yeah. Right? Now, match the numbers with the units. How many minutes in a second or how many seconds in a minute? 60 seconds is 1 minute. There you have it. So you can do that conversion. I'm going to do it the easy way. I'm going to wipe out a 0 there and there. That's dividing by 10. And I'm going to divide 6 into 15, or 150. 6 will go into 15 twice with 3 left over. That's 25, isn't it? Okay. So that'll be 20. What's that? If you got a calculator, just divide 1,500 by 60. That'll work too. But I was doing it in my head, so that's 25.0 kilograms per second. You need 3 digits, so I'll put the 0.0 there. Okay? Now. Yeah, because we need 3 digits, right? All right. So, that gives us mass per second, okay? We really don't want mass per second. We want force per second. How do we get from kilogram per second to, what's the unit for force in the SI system? Named after Newton, exactly. Okay, so to get that, we're going to have to multiply by 9.80 meters per second squared. Okay, so multiply your 25.0 times 9.80, and what do you get? A little louder. 245? 245, and that will be Newton per second. Okay? Because a Newton is a kilogram meter per second squared. Kilogram meter per second squared is a Newton. So it's Newtons per second. Okay? But we need to get work. And work is a force times a distance. And what distance do we have here? .0 meters. So multiply this by 45.0 meters. And what does that give us? To 0.25? Is that what you got? 11,025. And that would be Newton meter is a joule per second. But what's a joule per second? It's a what? A watt. A what? Yeah, a watt. Okay. So there we have how many watts? So this is 11,025 joules per second, which is 11,000, why did I write that again? 11,025 watts, okay? Now, we want it in kilowatts, so what have we got to do? Second? By what? Oh, really? Kilo means 1,000. So 11,000 would be 11.0 kilowatts. Basically, you're dividing by 1,000. You're going from a big number in a small unit to a small number in a big unit. Okay? So that'd be 11 point. Now we only want 3 significant digits. 1, 2, 3, look to the right, 2, that's small, drop it. 11.0 kilowatts. That's what they wanted. There's your power. Okay? One bite at a time. All right? Oh my goodness, how could it be? And let's see what they got. They got 11.02. Good for them.
You get different ones, each one, but it's like we still should have probably went over, on the example, we should have went over another different one. I'm just saying, because you did all 5 examples. We still kind of trying to figure out what the first one is. We should have probably did more examples of the first one before we had moved to the next one.
Okay. Maybe then it'd be a good idea to do something for homework.
I mean,
I see.
I'm just saying, I did the other homework.
Yeah. Okay. I would say, and they have odd answers in the book, do either 1 or 3. They're very similar. You can do them both if you want to. Then do any of the odds 5 through 25. And I'd say do some of every type. So you read through it and say, oh, that's the same as last, move on to something else. Okay? And next time we'll pick up with energy on page 8.3. Any questions?